Good morning. Today we are discussing about an interesting topic in particle physics, that is quarks or Quark model. This topic arises with the question that what are the building blocks of matter? We know that the matter is made up of atoms, and inside the atom we know that there is a nucleus with electrons outside and protons and neutrons inside. So we considered electrons, protons and neutrons as the building blocks of matter, and we named it as fundamental elementary particles. And there are several other elementary particles also, like pions, kaons, photons, gravitons and resonant particles. They were also termed as fundamental elementary particles. But there are some particles which are more fundamental than elementary particles. Why we had named elementary particles as elementary particles? Because they are structureless. We don't know the structure of that particles. So that we had named that particles as elementary particles. They cannot be explained with the help of other particles. So they are fundamental elementary particles. But the developments and researchers in theoretical physics predicted that there are some particles which are more fundamental than elementary particles. And such particles are called quarks, which is our today's topic. So quarks are the building blocks of hadrons. Hadrons, we know that in the last class, in the classification of elementary particles, we had seen that the baryons and mesons together known as hadrons. So these hadrons are made up of quarks. So we can define quarks as the building blocks of hadrons. This concept was given by Murray-Gell-Mann in 1964 and also by G. Zweig. And the name quarks was given by Murray-Gell-Mann and Zweig gave it the name ACE. And initially only 3 types of quarks were labeled. So the 3 types of quarks are up quark U, down quark, the symbol is D, and strange quark S. You know the word strange. In the last class we had discussed about the strange particles and also the strangeness quantum number. Kaons and hyperons are together known as strange particles, and these strange particles are assigned a quantum number called strangeness quantum number, and here we are having another quark known as strange quark. So the strange particles is made with at least one strange quark. We will discuss it later. So the basic building blocks of hadrons are quarks, and the 3 types of quarks are up quark, down quark and strange quark. Now let's study in detail about these quarks. We know that we had studied the concept of quantization of electric charge, isn't it? Quantization means capital Q is equal to plus or minus NE. That means the charges can be an integral multiple of the basic unit of charge E. That gives you the quantization of electric charge. That means that a charge can have positive values, negative values, and only the integral values. That means 1e, 2e, 3e, minus 5e, minus 7e, etc. So we know that the charges can have only the integral values of E, and that concept is known as the quantization of electric charge. Different from that concept, all quarks are having fractional charges. Up quark is having charge 2 by 3e. Down quark is having charge minus 1 by 3e. And S quark is having charge minus 1 by 3e. So all quarks have fractional charges. Now what about the spin of the quarks? All quarks have half integral spin. That is, all quarks having the spin value 1 by 2 h cut. And we know that we had studied in the last class that the particles having half integral spin are called fermions. So we can say that quarks are fermions. And in related with a particle, will be an antiparticle also. Similar to that, quarks are having their antiparticles called antiquarks, given by U bar, D bar and S bar. We know that the charge of U quark is 2 by 3e. Then what will be the charge of U bar, anti quark? It will be minus 2 by 3e. And the charge of D bar will be 1 by 3e. Also, the strange quark S is having charge minus 1 by 3e. That means the anti-quark will have a charge, S bar will have a charge 1 by 3e. Now we had said that quarks are the basic building blocks of hadrons. That means hadrons are made up of quarks. And we know that hadrons are both baryons and mesons. Now, all baryons are made up of 3 quarks. So, what will be the baryon number of each quark? All baryons are made up of 3 quarks, means the baryon number of each quark will be 1 by 3. For example, you can see a proton is made up of 2 U quark and a D quark. That means proton is made up of D quarks. So let's check for the charge conservation, whether the charge is conserved or not. We know that the proton is having positive E charge. So let's add the charges of the individual quarks. That is U having 2 by 3e, again U having 2 by 3e and D having minus 1 by 3e. So adding you will get E, that is the charge of a proton. So proton is composed of 2 U quark and a D quark. Now another baryon is neutron. And neutron is made up of 1 U quark and 2 D quark. UDD. So adding the charges 2 by 3e plus minus 1 by 3e plus minus 1 by 3e will give you 0. That means the charge of neutron is 0. So the examples for baryons are proton and neutron having quark composition P is equal to UUD and N neutron is equal to UDD. So all the baryons are made up of 3 quarks. Now what about mesons? Mesons are made up of 2 quarks. One quark and then antiquark. So all mesons are made up of one quark and one antiquark. We know that mesons consist of pions, kaons and eta mesons. Let's go for 2 examples. Pi plus pion is made up of U quark and anti-D quark, that is D bar. U D bar, that means one quark and one antiquark for pi plus meson. Again you can check for the charge. U is having 2 by 3e and D is having charge minus 1 by 3e. So D bar will having charge 1 plus 1 by 3e. So adding you will get E, that is the charge of a positively charged pion. Pi plus is having charge plus E. Next example is K plus. K plus, you know that K having positive charge. So plus E will be its charge and its composition, quark composition is US bar. U is having charge 2 by 3e. S is having charge minus 1 by 3e. So that S bar is having charge plus 1 by 3e. So adding you will get E, that is the positively charged kaon. See, one thing you have to note here. Kaon is a strange particle, isn't it? So strange particle will contain at least a strange quark. So K plus is having S bar. Strange quark or it's a antiquark, S or S bar. So all the strange particles, you know that the strange particles are kaons and hyperons. So all the strange particles will contain at least one S quark or S bar quark. And with this concept of quark, Murray-Gell-Mann found out the quark composition of omega minus particle, and omega minus is composed of 3 S quarks, SSS, and for this he got Nobel Prize in 1969. Later on, 3 more quarks also added to this quark family. They are charm, C, having charge 2 by 3e and spin half h cut. Now the next quark is top or truth and the symbol is T, again with the charge 2 by 3e and spin half. And the 6th quark is bottom or beauty with the symbol B, having charge minus 1 by 3e and spin half h cut. So altogether now this quark family consists of 6 quarks: up, down, strange, charm, top or truth, bottom or beauty. Now the next topic regarding this quark is flavor of quarks. We know that now this quark family consists of 6 quarks, but when we consider a particle family, that consists of its antiparticles also, isn't it? So this quark family consists of 6 quarks and their antiquarks. So 6 quarks with their 6 antiquarks forms 12 members in a quark family. So we can consider these 12 members as 12 different states of a same particle or a single quark. In the last class we had discussed that we can consider proton and neutron to be two different states of a single nucleon. Similar to that, here also we can consider a single quark, and the 12 different quarks are the 12 different states of that single quark. And these different states are called flavors of quark. When we talk about the term flavors, what will come into your mind? Yeah, ice cream. Now, what is the speciality of the ice cream? Ice cream is one item, isn't it? One food item. But it is having different flavors, isn't it? So the item is one, but having several flavors. Similar to that, here also we can consider a single particle or single quark, and it is having different flavors or different states. So 12 different states of a single quark. So these different states are called flavors of quark. So there are altogether 12 flavors of quark and antiquark. The 6 quarks plus 6 antiquarks forms the 12 members of a quark family, and these 12 members can be considered as the 12 different states of a single quark called flavors of quark. Now, what is meant by color of quarks? We know that omega minus is composed of 3 s quarks, isn't it? 3 s quarks means each s quark is having spin half h cut. So altogether the spin is half h cut plus half h cut plus half h cut, that is 3 by 2 h cut. So 3 by 2 h cut is the spin of omega minus particle. So we know that these quarks are, since the quarks are having half integral spin, these quarks are called fermions. And the fermions must obey Pauli's exclusion principle. We know that electrons are also fermions, and we know that this electrons obeys Pauli's exclusion principle, isn't it? Similar to that, since the quarks are fermions, quarks must obey the Pauli's exclusion principle. That means no two fermions can be in the same state. So here omega minus is having 3 s quarks, and each s quark is having spin half h cut. But there is a problem that these s quarks must obey the Pauli's exclusion principle, that no two fermions can be in the same state also. So how can one have more than one quark in the same spin state? In order to solve this problem, a new property is assigned, given by C, and C can have values C1, C2, C3. See, we had solved that Pauli's exclusion principle for electron with the help of spin, isn't it? Electron can have two spin states, that is spin up or spin down, so that no two electrons will not be in the same state. The two electrons in the same state will have opposite spins. That's how we had solved the problem of electrons being in the same spin state, by introducing spin up and spin down state. So here also we are having a problem that omega minus is having 3 s quarks, and these 3 s quarks is having same spin, and they are in the same state. violating the Pauli's exclusion principle. So how we can remedy this, we can solve this problem? So we had thought that we can assign a new property called C, and this C can have values it can have three values, C1, C2, C3, like that of spin up and spin down state of an electron, so that each S quark will occupy different states like half H cut C1, half H cut C2, half H cut C3. That means the three S quarks in omega hyperon should occupy different states like half H cut C1. The state of the first S quark is given by half H cut C1, and the state of second S quark given by half H cut C2, and the third S quark with half H cut C3. So even though the spins are the same, they are having a different property, that is C1, C2, C3. So they can reside in the same state, since the property C is different for three S quarks. And this concept was first proposed by Oscar Greenberg and also by another one called Nambu. And Nambu defined C as color. So we had given a new property and we didn't give it a name, but Nambu had given the name color for C. So each S quark in omega, even though the S quark are the same with same spin, that is half H cut, each S quark is having a different property called color given by C1, C2, C3. And since Nambu gave it a name color, we can just compare it with the colors we have. So the C1, C2, C3 are replaced with red, green and blue. Think that there is no relation with the physical colors we have. In order to distinguish between the different states of S quark in omega minus, we are giving this new property, and this new property is just having a name color. It has nothing to do with the physical color. We are giving it the name of physical colors in order to distinguish us, to help us to distinguish between these three S quarks. So each quark comes in three colors, red, green and blue, so that they are having anti-colors like anti-red, anti-green and anti-blue. So in omega minus hyperon, we have three quarks, means one of the quark will be red, other will be green and the third one will be blue. So three S quarks all having the same spin half H cut, but their color is different, means they can reside in a same state. So according to the color property assigned to quarks, all the three quarks in baryon have different colors, which satisfies the Pauli's exclusion principle. So we had initially started a question that how can three S quarks can exist in the same state. So we had given a property called color, and this color for three S quarks are different, so that they can stay in a same state without violating the Pauli's exclusion principle. And we know that red, blue and green when joined together will become white, isn't it? So we had considered omega hyperon, which is a baryon that consists of three quarks, three S quarks. So the color of first quark will be red, second one will be green and the third one will be blue. So the baryons are white in color, or we can say colorless. Similarly, an antibaryon. So think of omega minus bar. Omega minus bar will be having three anti-S quarks. That means S bar, S bar, S bar. That means the color of each S bar quark will be anti-red, anti-green and anti-blue quark. So that's about a baryon. Now what about a meson? We know that a meson is made up of a quark and an anti-quark. So a quark of one color and an antiquark of the corresponding anticolor, isn't it? So again, mesons also will become colorless. So we can say that hadrons and antihadrons are colorless. We know that red and green and blue together forms white. And we also know that R and R bar give you white. So what will be R bar? Anti-red will be green. Comparing with the first equation, anti-red will be green plus blue, that is cyan. That will be the color of peacock blue. This is to know how we interpret anti-colors, like R bar is peacock blue, G bar is magenta and B bar is yellow. So this is to know that how the anti-colors exist for each quarks. And remember that the color property has no connection with our colors. It's just a property given to the quarks in order to distinguish them between different, or in order to distinguish them in the same state, or not to violate the Pauli's exclusion principle. Now, what is quark confinement? We had said that baryons, proton is made up of UUD and neutron is made up of UDD. So initially we know that there was atoms, and inside the atomic structure we know that there is a nucleus. Now we had said that this nucleus, nucleons, that is protons and neutrons, are made up of quarks. So can we see these quarks when we tear the proton or neutron apart? How can we see the quarks? The answer is the quarks are permanently imprisoned inside, and that is known as quark confinement. So what happens when we provide more energy to the nucleus? We know that when more and more energy is provided to the nucleus, electron will absorb that energy and will get out of the atom. But when we provide more and more energy to the nucleus of an atom, what happens? We can think that this proton and neutron will escape, isn't it? Or we can think that they will split into their components, quark components. We know that a proton is made up of 2 U quark and D quark, and neutron is made up of 1 U quark and 2 D quark. So what if we are providing more energy to this proton and neutron, we can see the structure of proton and neutron, or we can think that this proton and neutron gets divided and we can see the quarks, isn't it? But it's not like that. When enough energy is given, instead of quark breaking free from the others in a hadron, the excess energy goes into producing a quark and an antiquark pair. That means a quark-antiquark pair means a meson is formed. Think that I am providing more and more energy to neutron, so that I wanted to split the neutron and I have to see the structure of the neutron. And I know that this neutron is made up of U and DD quarks. So I am giving the energy to see the quark composition of neutron. So I am providing more energy with the help of a gamma ray, that is gamma plus neutron. What happens is that I am not getting any sign of quarks, but a pair of quark-antiquark pair is formed. That means a meson is formed. So you can see that this is the picture. So UDD is a neutron, and I am giving it an energy with the help of a photon. So what happens? Inside the neutron, a new quark-antiquark pair is formed, that is U bar. So along with UDD, a new quark and an antiquark is formed inside, that is U and U bar. Now all these quarks rearrange themselves. So what happens? Now UDD becomes UUD and the remaining quark is U bar D. And you know that UUD is proton and U bar D is, that is a quark and an antiquark pair. That means it's a meson, that is pi plus meson. So back to our equation, when we are providing more energy to neutron, that is gamma plus neutron, it will form another particle, that is proton, along with a meson, that is pi minus meson. So when enough energy is given, instead of a quark breaking free from the others in a hadron, the excess energy goes into producing a quark-antiquark pair, and thus a meson is formed. Now what happens when we increase the distance between two quarks? When we try to increase, if we want to split the quarks, we have to provide more energy, so that the distance between these quarks must be increased so that get detached and we can see the quarks, isn't it? So the more we increase the distance between two quarks, the harder it becomes to separate them further. That means whenever we provide more energy to increase the distance between the quarks, the force between them increases. The force that exists between the quarks increases as we try to increase the distance between two quarks. So we cannot separate the quarks anymore. So we can see that these quarks are permanently imprisoned inside, which is known as quark confinement. And the force that binds the two quarks is called color force. See, we know that this proton is made up of UUD and neutron is made up of UDD. So there is a force that holds these quarks together, and that force is known as color force. And whenever there is a force exists between two particles, there must be a particle that gets exchanged between them, and that particles are known as gluons. I repeat, whenever there is a force exists between two particles, there must be an exchanging particle between them. So we know that a color force exists between two quarks. So if there is this color force, there must be an exchanging particle between these quarks, and these exchanging particles are known as gluons. So gluons are the particles responsible for the interaction of quarks holding together to form hadrons. So the gluons is exchanged between two quarks, so that this color force exists between the quarks, and this color force bind the quarks together to form hadrons. And these gluons, what are the properties of these gluons? Gluons are massless and they travel with the speed of light, that means travels at c. Again, it carries a color and an anticolor. And there are 8 gluons, so that whenever there is an interaction between two quarks, we know that there is an interaction and there is a color force. So what happens is that gluons are continuously emitted as well as absorbed by the two quarks, between any two quarks. So 8 gluons are there. So the emission or absorption of a gluon by a quark changes the quark color. And we can consider this color. We had defined, or we had know what is color for quarks. Now this color is like charge. Quarks have color charge. We know that the charges produce field, isn't it? We know that if an electric charge is placed at a point, there is a region around that electric charge where we can experience a force. That field is known as electric field, isn't it? If the quark is having color charges, these color charge will produce color field. And the quantum theory of color field is called quantum chromodynamics, QCD. And we know that there is a force exists between these two quarks, between any two quarks, and that force is known as color force. Color force associated with the color field not only binds the quarks to form a baryon or meson, but it also links the quarks residing in different particles. That means it holds the quarks together to form a hadron, as well as it also links the quarks residing in different particles. Or we can say these carriers of the color force, as we said earlier that these carriers of color force are called gluons, and these gluons are the quanta of color field. Quanta means it's an energy related term, isn't it? So it is the quanta of color field. So quarks are having color force between them, and gluons are the exchanging particles between the quarks, and gluons are the quanta of color field. Since the quarks are having color charges, there is a color field produced by these color charges, and the quanta of this color field is called are the gluons. So that's about the quark model. Hadrons are made up of quarks. There are 6 quarks and their antiquarks, each having charge and spin. Quarks are fermions. Baryons are made up of 3 quarks. Meson is made up of a quark-antiquark pair. And this 12 different quarks can be considered as 12 different states of a single quark called flavors. So these 12 different states are called flavors of quark. Now in order to distinguish between the same quarks in a state, we have assigned a new property called color, so that the Pauli's exclusion principle is not violated. And this color comes in 3 ways: red, blue and green, with their anti-colors as anti-red, anti-blue and anti-green. Now we cannot see the quarks if we tear or if we try to separate the if we try to tear the proton or neutron. Since if we are giving more and more energy, what happens is that it will produce a quark-antiquark pair. That means a meson is produced. When we try to increase the distance between the quarks by just thinking that pulling the quarks away from each other, what happens that the force that binds the quarks together will increase. So we cannot separate the quarks. So that concept is known as quark confinement. Now there exists a force between the quarks that helps to bind them together. That force is known as color force. And the quarks are having color charges that produces color field. So if there is a color force between these charges, between quarks, there is an exchanging particle between them called gluons. So gluons are the quanta of color field. An important essay question. So study properly. Thank you.